So good afternoon, dear participants. We are starting with the part 2 of energy materials lecture, which will be covering batteries and supercapacitors. So last Friday, what we did was the part 1, where we talked a little bit about electrochemistry and all the different backgrounds and the different definitions and the concepts which needed to be revised before we actually delved deeper into the battery. And today we will be covering more about the batteries, the electrode materials. So overview of today's talk will include cathode materials for lithium-ion batteries. Then we will talk a little bit about anode materials for lithium-ion batteries. Then we will move on to cell characterization. And in today's lecture, we'll be covering two different types of cell characterization techniques. One is cyclic voltammetry, or CV as it is popularly known, and how you are characterizing batteries using charging and discharging cycles. So with this, let's start with the cathode materials for LIV. If you remember, in the last class, we had spoken about the different materials which were explored by Professor John B. Goodenough and also Professor Whittingham and Professor Akira regarding the development of the lithium-ion batteries. So the birth of the rechargeable lithium batteries is actually indebted to intercalation chemistry. And intercalation chemistry, it basically involves reaction between guest molecules or ions with solid host. And this has been known for almost now 180 years. So Schoftel was the first to show the intercalation of sulfate ions in graphite in 1841. So way back, this intercalation of some ions into graphite was actually discussed, and it was also shown. So these rechargeable lithium batteries, if you remember when we were talking about in the last class, one of the biggest problem was with the lithium anode. So as long as the lithium anode was there, the biggest problem is the formation of these dendrites or the whiskers. And if the dendrites form while the movement of the lithium ions take place from the cathode and the anode, then there is a chance of a short circuit happening. And that is the reason why the cyclability of the lithium ion batteries were very poor. Now, to take care of that, basically, it was the Japanese professor who decided that instead of lithium, why don't we use graphite? Because graphite has intercalation capability and lithium can intercalate into graphite. So that was the turning point, the biggest turning point, and which led to the birth of rechargeable lithium batteries. So if you look into the past, Whittingham, he demonstrated the first rechargeable lithium battery at Exxon Corporation in the United States with a titanium sulfide cathode, a lithium metal anode, and a liquid electrolyte in which a lithium salt like lithium chlorate was dissolved in an organic solvent, which was glyme dimethoxyethane, which is glyme, and tetrahydrofuran, which is THF. So what were the problems of this? For this particular battery, Whittingham found that the cell voltage was limited to less than 2.5 volt. So obviously the energy density is less, because if you remember what we had discussed, energy density is nothing but a product of the specific capacity, which is multiplied by the potential difference which you have. In this case, the cell voltage or the cell potential is limited to 2.5 volts. So obviously the energy density is less. And then another problem with the TiS2 cathode was the dendrite growth on lithium metal anodes during cell cycling, which caused internal shorting and presented a fire hazard. So now this had to be taken care of. So using sulfide, this was the biggest problem. So this led, basically, this problem with sulfides actually became the genesis of the birth of these kind of oxide cathodes, which you still find today in all the commercial batteries. So as I said, the cell voltage is determined by the energy difference between the redox energies of the anode and the cathode. So what is that? The cathode energy, it should lie as low as possible, whereas the anode energy should lie as high as possible. So that means what? It means basically the cathode would require stabilization of higher oxidation states with a lower lying energy band, whereas anode would require the stabilization of lower oxidation states with a higher lying energy band. Now what is the problem? The problem is how we can access this lower lying energy band of a metal ion with high enough oxidation states in a material so that the cell voltage can be increased. So how do you do that? With sulfide, this is definitely a problem. So Goodenough, what he did, Professor Goodenough, he utilized the basic understanding of this point that the top of a S2 minus 3p band, it lies at a higher energy than the top of a O2 minus 2p band. And this basically, this simple concept of inorganic chemistry he used to design these oxide cathodes. Now on the left hand side, what you see is a figure where you have the energy versus the density of states. And what you see over here is the topmost part, there's the highest potential. What you have is lithium versus lithium plus. This is followed right below that it is graphite. That is why graphite is basically a good anode material for all these different lithium ion batteries. But go below and what you find is when you have titanium 3 plus 4 plus T2G, if you look into the oxide and you look into the sulfide, what you find is that when you are actually pitching a lithium against this titanium sulfide, on the left hand side, the voltage limit is only 2.5 volt. On the left hand side, you can see over here. Whereas if you look into the other different kinds of these transition metal ions like Mn3 plus 4 plus, then you have Ni3 plus Ni4 plus, then you have CO3 plus CO4 plus. If you look into the sulfides and you look into the oxides, you will find that the oxides actually have a much lower potential compared to that of the sulfides. So the top of the S2 minus 3p band, it lies at a higher energy limit and it limits the cell voltage less than 2.5 volt with a sulfide cathode. And the access to lower lying energy bands with higher oxidation states such as that of cobalt 3 plus 4 plus, and hence the higher cell voltage will be limited by the top of the S2 minus 3p band, and attempts to lower the cathode redox energy by accessing higher oxidation states in a sulfide, it will result in an oxidation of the S2 minus ion to molecular disulfide ion. So that is the reason why these are unstable. So the moment you want to have a cobalt sulfide, it will not actually be stable. It will kind of decompose, and with that, what is going to happen is you are going to lose your lithium. In contrast to that, what is happening? The top of that O2 minus 2p band lying at a lower energy, it enables access to lower lying energy bands with higher oxidation state, and it increases the cell voltage substantially to 4 volt. So that is why on the left hand side, if you see over here, what you have is the voltage is around 2.5 volt, whereas when you go to cobalt oxide, that is lithium cobalt oxide, in that case, this energy gap, this voltage, it goes right up to around 4 volts. And if the voltage is increasing, then automatically the energy density of your battery is increasing. Okay. So with this, it actually gave rise to discovery of 3 different classes of oxide cathodes in 1980s. So one is on this, whatever you see is the layered lithium cobalt oxide. This has an octahedral side lithium ion, which offered an increase in the cell voltage from less than 2.5 volts in TiS2 to around 4 volts. So when it was started, first the kind of the reversible movement of lithium ions from the cathode to the anode, it was shown in titanium sulfide, but the voltage was only 2.5 volts. Whereas when you moved up to lithium cobalt oxide, when you instead of sulfide you changed it to oxide, in that case the voltage increased to around, or the potential increased to around 4 volts. Then you have another system of oxide cathodes, which are the spinels. So spinel LiMn2O4 with tetrahedral site lithium ions, they offered an increase in the cell voltage from 3 volts for octahedral site lithium ions with a manganese 3 plus 4 plus coupled to 4 volt with an accompanying cost reduction. So in this case, actually, you are getting rid of the cobalt, which is expensive and also toxic. Instead of that, you are having earth abundant manganese in this case. And obviously, so this leads to a cost reduction also. And the other class of the oxide cathodes which are having are nothing but the polyanionic oxides. So like lithium ferrous sulfate, they offered yet another way to increase the cell voltage through inductive effect, as we had discussed in the last class. Inductive effect, it actually gives rise to an increase in the cell voltage. So the cell voltage increases from less than 2.5 volt in simple oxide like iron oxide to 3.6 volt in case of lithium ion sulfate, with a further reduction in cost and improved thermal stability and safety. So if you look today at what are the different classes of cathode materials which we can consider in case of lithium ion batteries, these are the layered lithium cobalt oxide, then you have spinel lithium manganese oxide, otherwise you can also use polyanion lithium ion sulfate, molybdates, tungstates, as the case may be. So what is the cathode class 1? We will discuss a little bit in details, which are the layered oxides. You look into the right hand side, you have this particular structure where these red balls are nothing but lithium, whereas the green ones which you see inside, these are the cobalt, and the dark blue ones are nothing but your oxygen. So in layered lithium cobalt oxide, monovalent lithium and trivalent cobalt 3 plus ions, they are ordered on the alternate 1-1-1 planes, as you can see, of the Roxford structure with a cubic close packed array of oxide ions. And this particular structure, what we know, is known as the O3 structure. So the large charge and the size differences between lithium and cobalt ions, it lead to a good cation ordering. And this is very critical to support the fast two-dimensional lithium ion diffusion and conductivity in the lithium plane. Okay, so this helps, this supports in the fast lithium ion diffusion and conductivity. Now, when you're having this good cation ordering, there is a direct cobalt-cobalt interaction across the shared octahedral edges in the cobalt plane, and this facilitates good electronic conductivity as well. So you have good lithium ion diffusion and conductivity in the lithium plane. Along with it, you also have a very good electronic conductivity. Now this Li1 minus X CO2, it becomes metallic on charging due to the introduction of holes into this low spin CO3 plus 4 plus T2G6 minus X band. And the good structural stability along with high electrical and lithium ion conductivity offers fast charge discharge characteristics with very good reversibility. So that is the reason why lithium cobalt oxide remains as one of the best cathodes to date with a high operating voltage of around 4 volts. But all is not good. The problem is that there is the practical capacity of lithium cobalt oxide is limited to 140 milliampere hour per gram. Actually, if you look into the theoretical capacity, this is around 280, but you can get only half of it, because if you move more than 0.5 of the lithium ion from the lithium cobalt oxide structure, the structure crumbles. So that is why the practical capacity of LiCO2 is limited to around 140 milliampere hours per gram. Now let's look into this. Now this LiCO2 is nothing but a part of that LiMO2 oxide, right? This all of which crystallizes in the O3 layered structure like LiCO2. So you can have M3 plus ion. What are the different transition metal ions you can have? You can look over here. You can have scandium, you can have titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and copper. Out of this, how many are crystallizing in the O3 layered structure? Scandium you will not get, but you have titanium, vanadium, chromium, cobalt, nickel, which are basically crystallizing in this O3 layered structure. So now you have to remember, when this M is vanadium, manganese, and iron, these members, that is lithium vanadium oxide, lithium manganese oxide, lithium iron oxide, they suffer from layered to spinel transition. So the layered structure, they kind of they become unstable and they become a spinel structure or other structural changes during the charge process. So when you are removing the lithium from this vanadium, manganese, and iron oxide, lithium, vanadium, or lithium, manganese, or lithium iron oxide, what happens is that instead of staying in that layered structure, there is a crumbling of the structure, the change in the structure, either it forms spinel or some other structure, and that is why there is a destabilization of the structure. And this is due to the low octahedral site stabilization energy. So these are not very good cathodes. Because to become a good cathode, one of the most important points is that when the lithium is moving from the structure, then the structure should be able to hold, so that when the lithium is coming back into it, it is able to again get back into its original form. And that gives rise to reversibility. The moment the structure changes, your cathode is becoming irreversible. The process is becoming irreversible. You are losing lithium. And obviously the capacity is going to fall. The cyclability is going to be very poor. So now looking into this, you also have titanium, which has a layered structure. So lithium titanium oxide can also be a good layered cathode, but it is not the case. Why? Because it operates at a lower voltage and it is also very tedious to synthesize. Similarly, lithium chromium oxide also has a layered structure, but it is difficult to charge. Why? Because it displays a large polarization with an increase in the charge voltage. So if it is highly polarized, then again, it is not very much a good cathode material. You need a large polarization, means the irreversibility factor is very high. So obviously, I mean, this is then not a very good cathode material. Then you have lithium nickel oxide also. This also forms a layered structure. But the problem is that it is difficult to synthesize as a well-ordered material. Why is this so? Because this nickel 3 plus, when you are having LiNiO2, nickel is in the form of 3 plus, and this tends to be reduced to Ni2 plus. So what you will get is, you will get lithium deficient structure at a high temperature synthesis condition of 700 to 800 degrees centigrade. And this is accompanied by volatilization of some of the lithium ions from the reaction mixture. So obviously lithium is moving out. then the structure is not exactly LiNiO2. What you get is Li1 minus Y, Ni1 plus YO2, and this is not as good as the one as LiCO2. So now if you compare the crystal field stabilization energies of the transition metal ions in this different kinds of cathodes, NMC is nickel, manganese, and cobalt. So you have, instead of lithium cobalt oxide, you are putting in some amount of nickel and manganese in this kind of cathodes. So what happens is over here, as you can see, cobalt, it has a very high octahedral side stabilization energy, whereas manganese has a very less amount of octahedral side stabilization energy. So this will give rise to some kind of structural or instability, which we will see later on. But the main idea is, instead of LiCO2, because cobalt is anyway, it is a problematic material in the sense that the distribution of cobalt in the Earth's crust is not very equitable. So only a few countries have access to all these cobalt mines. And what happens is cobalt is also very expensive. So if you can reduce, and it is not that much abundantly available as that of iron or manganese or nickel. So for that reason, it is better to have less amount of cobalt. And by reducing the amount of cobalt and adding in some other material, if you are still able to maintain the electrochemical performance, then nothing like it. And continuous research has shown that you can use nickel and manganese as a substituent for cobalt. So you can actually reduce the amount of cobalt and you can add in some amount of nickel and manganese. And these cathodes are known as the NMC cathodes. So what is the genesis of this lithium, nickel, manganese, cobalt oxide cathodes? So you reduce the cobalt content by adding nickel and manganese. So cost goes down and the capacity increases. What happens in NMC is this Mn3 plus tends to get oxidized during synthesis to Mn4 plus by reducing this nickel 3 plus to nickel 2 plus. And the reason is that the manganese 3 plus and 4 plus band lies above the nickel 2 plus 3 plus band. Thus, Mn4 plus helps the incorporation of nickel as a stable Ni2 plus into NMC and serves as a structural stabilizer without participating in the charge discharge process. So the problem which we had seen in LiNiO2, that it doesn't stay as Ni3 plus and it goes into Ni2 plus structure, by having a little bit of manganese as well as cobalt along with the nickel in NMC cathode, what happens is you can stabilize this nickel. So manganese, now if you look into the comparison of the characteristics of manganese, cobalt and nickel in NMC cathode, you see the chemical stability of manganese is more than that of cobalt. Nickel actually falls in between manganese and cobalt for all these different characteristics. So chemical stability of manganese is more than cobalt, structural stability of cobalt is more than manganese, electrical conductivity of cobalt is more than manganese, abundance of manganese is more than cobalt, and environmental benignity of manganese is more than cobalt. So these are the characteristics. So now you have to see that manganese does not suffer any chemical instability involving oxygen release from the lattice, in contrast to cobalt, as the cobalt 3 plus 4 plus band overlaps with the top of the O2 minus 2p band. This you remember in the previous slides we had shown, where we had shown the potential as per the density of states value. So manganese, but though manganese doesn't suffer from any chemical instability, it suffers from structural instability. Why? Because it can readily migrate from the octahedral site in the transition metal plane to the octahedral site in the lithium plane through a neighboring tetrahedral site due to the smaller octahedral site stabilization energy, resulting in a layered to spinel transition and accompanying voltage decay during cycling. In contrast to it, what happens? Cobalt enjoys a very good structural stability without such cation migration due to the large octahedral site stabilization energy. Now, in addition to the above two critical differences, cobalt 3 plus 4 plus becomes metallic on charging due to the partially filled T2G orbitals interacting along the shared edges, while manganese 4 plus, it remains semiconducting. Also, manganese is abundant and environmentally benign compared to that of cobalt. Now, interestingly, we know that nickel is lying between manganese and cobalt in all the 5 criteria, as shown in table over here, as you can see. The reason is why? Because nickel 3 plus 4 plus band barely touches the top of the oxygen O2 minus 2p band, so that nickel 3 plus can be charged all the way to nickel 4 plus without removal of electron density from the O2 minus 2p band and loss of oxygen from the lattice. So it can go all the way up to Ni4 plus. And Ni3 plus, it exhibits an octahedral site stabilization energy value, which is intermediate between those of manganese 3 plus and cobalt 3 plus, offering reasonably good structural stability. Hence, this nickel-rich manganese NMC cathodes, this is right now the trend. So you keep on increasing the amount of nickel in this NMC cathodes. What is the problem? So if you say that, okay, fine, if I have to increase the amount of nickel and that helps, then why don't I use only LiNiO2 instead of LiCO2? Let me use only LiNiO2. So it's difficult to keep, the problem is that it is difficult to keep all nickel as nickel 3+ during the synthesis process at high temperatures, which is greater than, you need a high temperature to synthesize. So the existence of part of nickel as Ni2+ results in the volatilization of part of lithium and formation of a lithium deficient Li1- X Ni1+ XO2. So this implies a cation disorder between lithium and nickel and the presence of nickel in lithium layer, which impedes the rate capability. Also, LiNiO2, what it does, it undergoes a series of phase transitions during the charge-discharge process, particularly a deep charge involving the removal of a significant amount of lithium from the lattice. So again, this will lead to a degradation in the rate capability. And also you have to remember that nickel 4+ is highly oxidizing and reacts aggressively with the organic electrolytes used in the lithium-ion cells. So the reaction results in the formation of a very thick SEI layer, which again degrades the rate capability, increases the impedance, and consumes active lithium. So that is why we cannot use fully lithium nickel oxide. So we have to add more amount of nickel in the lithium cobalt oxide. So we have nickel rich NMC cathodes, but we cannot have a complete lithium nickel oxide as the cathode for LID. So the chemical instability of this highly oxidized nickel 4+ results in the transformation of the layered oxide to a rock salt, LiX Ni1- X O phase on the surface of LiNiO2. And the highly oxidized and unstable Ni4+ also causes concern with the thermal runaway. So there can be a thermal runaway if you have this highly oxidized, unstable Ni4+ in large amount in your system. So the push to increase the energy density, the potential to obtain higher capacity as Ni3+ could be oxidized all the way to Ni4+, and the unsolvable problem of the voltage decay associated with lithium-rich layered oxides have reinvigorated the interest in high nickel content oxides during the past few years. So let's have a kind of idea about the NMC cathodes. So why, so we know that NMC cathodes are better than that of LiCO2 cathodes. And nickel-rich ones are definitely the ones which people are right now researching very vigorously. But they have these 3 critical challenges. When you're having a nickel-rich NMC cathode, they have 3 critical challenges. One is cycle instability, then you have thermal instability, and you also have air instability. So this is all related to the instability of nickel 3+ or nickel 4+ in contact with the liquid organic electrolyte or ambient air. So the chemically unstable nickel 4+ ions that are generated on charging layered oxides with high nickel contents react aggressively with the electrolyte to form very thick solid electrolyte interface layers, along with the dissolution of nickel and manganese, which then migrate and deposit on the graphite anode, and it will limit the cyclability. And the transition metal deposition on graphite anodes catalyzes electrolyte decomposition, and it leads to the formation of a very thick SEI layer with a multi-layer structure, which increases with the increasing number of cycles as more transition metal ions dissolve and they keep on migrating to the anode. So this is the biggest problem of the nickel-rich NMC cathodes. So what happens is, after a specific number of cycles, the SEI layer thickness also increases with increasing nickel content due to the increasing transition metal dissolution and deposition on the graphite anode. Furthermore, the phase transitions occurring in the high nickel cathodes at a high state of charge with volume changes, they introduce cracks with new surface on cycling, which further exaggerate the surface reactivity with the electrolyte and increase metal dissolution and SEI formation, which results in a rapid capacity fade as cycling progresses. So all in all, what you have to understand is that whenever your material somehow is decomposing the electrolyte, what it is doing is it is actually taking away viable lithium from your system. If lithium, whatever, suppose you had X amount of lithium in the cathode and that X totally got transmitted to the anode storage over there, and then again when you are charging the system, it is again getting back and it is forming, when you are discharging the system, it is moving away from the anode and it is coming and resting in the cathode. That entire X amount of lithium has to come back to the cathode. The moment there is a loss, that means your capacity is decreasing, your cyclability is getting poor, your entire electrochemical performance is basically gradually it is degrading. Your entire performance is degrading. So this is a very important point. So you need SEI layer formation, obviously, because Coulombic efficiency is never 100%. There is an SEI layer formation which is needed, but if it continuously keeps on forming the SEI layer, you are losing your lithium, and that is not advisable. And whenever you're looking into NMC cathode, this is the part where you have to look at, that you have to prevent the decomposition of the electrolyte. So then how you can work on this system, how you can prevent this? So one is by intuitive bulk cation doping, as well as you can also stabilize the surface using various strategy to minimize the volume changes, crack formation and surface reactivity, which will help you overcome all these challenges in the cathode surface. So what you can do is substitute the transition metal ions with a small amount of inert ion like aluminium that makes the lattice robust by perturbing the long range metal-metal interaction. As I said, that cobalt-cobalt interaction which was there. The long range metal-metal interaction, you are perturbing it and increasing the metal-oxygen bond strength and thereby suppressing the metal ion dissolution. So you are suppressing the dissolution of the transition metal ions and in your electrolyte, because this transition metal ions are then going to deposit on the graphite surface, and it is going to take away precious space where your lithium can actually intercalate, and it is going to degrade your performance of both the cathode as well as the anode. So aluminium drastically suppresses this metal ion dissolution from the cathode, as the covalent aluminium oxide bonds keeps the oxygen tightly bonded, lowers the basicity and discourages transition metal ion dissolution by acidic atoms. So that is why right now, one of the important ways by which you can actually improve the cyclability of NMC cathodes, which are nickel rich, is by adding a little bit of aluminium to it, or inert ions to it. Now this was all about the lithium cobalt oxide or the layered cathodes and the NMC cathodes, which are currently being pursued vigorously for all the lithium ion battery technology. Then the second class of cathodes we'll talk about is the spinel oxides. Now in the spinel LiMn2O4, the manganese 3+, 4+ ions, they occupy the 16D octahedral sites, and the lithium ions, they are occupying the 8A tetrahedral sites of the spinel framework with a cubic closed pack array of oxide ions, as you can see over here. So the stable Mn2O4 framework with edge-shared octahedra, they offer a 3-dimensional lithium ion diffusion pathway with very fast lithium ion conductivity. You have to remember, in the layered structure, what you had is a 2-dimensional pathway, whereas in case of the spinels, what you're having is a 3-dimensional pathway. So the direct Mn-Mn interaction across the shared MnO6 octahedral edges, as in LiCO2 with mixed valent high spin Mn3+, 4+, T2G3, Eg1-X, in Li1-X Mn2O4 facilitates good hopping electronic conduction, but it remains as a small polar-ion semiconductor during the charge-discharge processes, unlike Li1-X CuO2. So it stays as a small polar-ion semiconductor, whereas if you remember, in case of cobalt, it was a metallic kind of a transition. So the insertion extraction of lithium into and from the tetrahedral sites with a deep site energy in Li1-X Mn2O4, it offers a very high operating voltage of 4 volt with a practical capacity of less than 130 milliampere hours per gram, as close to 1 lithium per 2 manganese ions can be reversibly extracted from the tetrahedral sites. So you see over here, what I have shown is the 2-dimensional lithium diffusion from one octahedral site to another octahedral site in the lithium plane through a neighboring empty tetrahedral site in O3 layered LiMnO2 cathode. So this is a 2-dimensional lithium ion diffusion. Whereas in case of your spinel, what you have a 3-dimensional lithium diffusion from one 8A tetrahedral site to another 8A tetrahedral site to a neighboring empty 16C octahedral site in the spinel cathodes. So this is the lithium ion diffusion, the lithium diffusion pathways in case of a layered structure, whereas in a spinel structure. But what is the problem in spinel oxides? One is the dissolution of manganese from the lattice into the electrolyte in presence of trace amount of hydronium ions. That is, if there is acidity in the, if the pH is low in the electrolyte, then there is going to be a disproportionation of manganese 3+ to manganese 4+ and manganese 2+ in acidic medium. So during such a disproportionation, Mn4+ gets retained in the solid, but Mn2+ is leached out into the solution. So in addition to degrading the cathode, because Mn2 plus is leaching out from your LiMn2O4 cathode, the Mn dissolution and its migration to the anode, it severely poisons the graphite anode and limits the cycle life of your lithium ion cells. But interestingly, if you substitute a small amount of the lithium, like around 5 atom% for manganese in LiMn2O4, it perturbs the long-range manganese-manganese interaction or contact. It frustrates the Mn3 plus disproportionation reaction, reduces manganese dissolution, and thereby improves the cyclability. So this dissolution of Mn2 plus, it can be stopped if you are substituting a small amount of the lithium with manganese. So basically, you are making it lithium deficient. Now, if you look into the other transition metals which has this kind of spinel structure, you have titanium which has a spinel structure, vanadium also has a spinel structure, manganese anyway you're using, the others don't have this kind of spinel structure. So what happens, why you cannot use Li2O4 or LiV2O4? Because Li2O4, it operates around 1.5 volts, so it is a not suitable cathode, voltage is very less, so obviously the energy density is going to be very poor. And LiV2O4, that lithium vanadate, it suffers from structural change and a lower voltage of around 3 volts. Whereas LiMn2O4, the voltage is very good, around 4 volts. And also the structural stability is more compared to that of LiV2O4. Now coming to the third class of the cathodes, whatever we are having, class 3 of the cathodes are the polyanionic oxides. So if you look into the operating voltage of isostructural iron molybdate, iron tungstate, and iron sulfate with that of iron oxide, all operating with the same Fe2 plus 3 plus couple, you will recognize the role of the counter anions. That is, what is the counter anion? One is MO6 plus, W6 plus, or S6 plus, which is drastically shifting the redox energy of the Fe2 plus 3 plus couple by altering the characteristics of the FeO bond. So in case of this iron molybdate, tungstate, and sulfate structure, the FeO6 octahedra share their corners with the molybdate or tungstate or the sulfate tetrahedra, providing an extended three-dimensional OFeOXOFeO linkage. So as a result, the more covalent molybdenum oxide or tungsten oxide or sulfur oxide bond, it weakens the iron oxide bond covalency through inductive effect, compared to that in that case of a simple iron oxide, that is Fe2O3. And this results in lowering of the Fe2 plus 3 plus redox energy. As you can see over here, it lowers that Fe2 plus 3 plus redox energy, and that is why the operating voltage it increases. So in case of iron sulfate, the operating voltage gets up to, it increases up to 3.6 volt compared to that of iron oxide, which is only less than 2.5 volts. So this is how it is going to look over here. In this case, you will find compared to lithium plus, when you are using Fe iron sulfate, this voltage is around 3.6 volt, which is definitely a plus point. So this olivine LiFePO4 was identified as a cathode in 1997. So this has become one of the very good cathode materials for lithium-ion batteries. The ability to increase the voltage drastically to as high as 5 volt in polyanionic cathodes, for example, in LiMPO4, even with the lower valent couples like CO2 plus 3 plus or Ni2 plus 3 plus, illustrates the power of the inductive effect imparted by changes in the metal-oxide bonding in tuning the operating voltages. So polyanionic oxides like lithium vanadium phosphate, sodium vanadium phosphate, sodium vanadium fluorophosphate, they have become very appealing cathodes for both lithium as well as sodium ion batteries too. Okay. So what are the advantages and disadvantages of these oxide cathodes? In case of layered and spinel oxides, you have very good electronic conductivity, you have closed pad structure with high densities, and you have very high volumetric density. In case of polyanionic oxide, what you have is poor electronic conductivity, lower densities, and lower volumetric density. So you will say that why I will go to polyanionic oxide, layered and spinel oxides are much better, but polyanionic oxides also has some plus points. They offer this important advantage of high thermal stability and better safety than the layered and spinel oxide cathodes, as in this case, the oxygen is tightly bound to phosphorus, sulfur, or silicon with very strong covalent bonds. Also, the polyanionic cathodes with optimally small particles coated with carbon, it can sustain high charge discharge rates due to good structural integrity, despite having a lower volumetric energy density. Moreover, polyanic cathodes, they are known with abundant transition metals like iron, unlike the layered and spinel oxides, offering sustainability advantages. So you have polyanic cathodes with iron also, which is a very earth abundant material. So it offers sustainability advantages. Therefore, they are appealing for grid storage of electricity produced from renewable energy sources like solar and wind. So you can use these kind of cathode materials like olivine, lithium iron phosphate, as cathode materials for lithium ion batteries, which can be used for all these different energy storage when you're having intermittent renewable energy supply. So it can help in stabilizing the grid. So this was all about the cathodes. Now we will move on to LIB anodes. So with an operating voltage close to that of lithium plus, which is around 0.1 volt, and a capacity of 372 ampere hours per kg, corresponding to the insertion of 1 lithium per 6 carbon atom to give LiC6, graphite has dominated as an anode in commercial lithium-ion cells. So what are the two important points when we are using graphite as anode? One is its operating voltage, which is as close as possible to that of lithium metal, and the other is its capacity. The capacity of 372 ampere hours per kg is calculated on the basis of the fact that when you are using graphite, 6 of the carbon actually intercalates 1 lithium. So with this kind of, so it results in the formation of LiC6, and using the formula which we had discussed in the last class, you can actually very easily come to this theoretical capacity, which is around 372 ampere hours per kg. So, but you have to also understand that all those, I had also discussed that, what should be the chemical potential of the cathode and the anode, and how electrolyte plays a very important role. And you ultimately lead to the formation of the SEI if these chemical potentials are not as per what is recommended for your electrolyte. So the redox energy of the graphite, if you see, it lies above the lowest unoccupied molecular orbital of the organic electrolytes used. And this leads to the formation of a stable solid electrolyte interface layer on the graphite surface in reaction with the electrolyte solvents. But this provides the stability for its operation with a very long time. But of course, the drawback is that you definitely lose some amount of the lithium whenever you're using lithium cobalt oxide or any other cathode material for the LIB. So because of the formation of the SEI, the Coulombic efficiency is never 100%, total 100%, but that SEI formation also helps because it provides stability on the anode. It prevents further disintegration of the anode. It provides a stability layer on the anode, and it also allows the movement of the lithium ions through it. Now, there are some other, like if you look into this particular thing, like in the insertion chemistry, what you have is graphite, which you can see the voltage is as close to lithium ion as possible. That's close to 0 volt, is almost 0.1 volt. Whereas you have some other kind of anode materials also, which works on this insertion chemistry. You have layered lithium titanates with you have this kind of lithium titanate structures where basically there is intercalation possible. And so this redox energy of alternative insertion reaction anodes like the Li4Ti5O12 with the spinel structure lies within the electrolyte stability window, and this doesn't lead to the formation of an SEI. So you see, graphite is actually falling outside this electrolyte stability window, whereas this lithium titanate is inside. So there will be no SEI formation with this. So the efficiency can increase, and there is a very negligible volume change. And this lithium titanate offers a very long cycle life. But there is a problem. Why? Because the operating voltage, if you see, is now around almost 1.5 volt versus lithium ion. So the capacity is very limited. So what you got in graphite was actually 372 ampere hour per kilogram. Compared to it in case of this Li4Ti5O12, you get a limited capacity of 160 ampere hour per kg. And so it reduces the cell energy density drastically. So this kind of anodes, it can be employed in cells for grid storage. Why? Because their energy density is not the important factor. You can have large bulky kind of batteries which can be actually kept for storage near the solar, the solar conversion plants or near the windmills. But when you are talking about like EV or something like, power electronics or something, then you cannot use this because at that particular point of time, energy density becomes very important. So let's find out the effect of structures on electrochemical potential of electrodes. So what are the benefits of nanomaterials? They lead to an enhancement of reversibility of lithium-ion insertion and extraction reaction in nanostructured electrodes without destroying the crystal structure. There is a reduction in the diffusion or transport distance of the lithium ions and electrons accompanying the lithium-ion insertion and extraction reactions if you have nanomaterials. Then there is a change in the site energy of lithium ions occupying the host lattice, which affects the electrochemical potential of the electrodes. So you can also introduce some defects, and let's see what are the defects, the effect the defects have on the electrochemical potential of electrodes. And these defects can be introduced through doping or atmosphere treatment and control of synthesis methods. So you have alien atoms which replace the inherent atoms in the host to produce cation or anion vacancies, which in turn affect the electrochemical performance of the electrode due to modified chemical pressure, lattice distortion, or change in crystal field. So to maintain the electroneutrality, oxygen vacancies produced which play a role in the nucleation for phase transitions which benefit the rate capability of electrode materials. So the lower valence nickel in place of higher valence vanadium can effectively decrease the electrostatic repulsion between the cations, thus decreasing the lithium site energy and increasing the potential of the doped material. So this is exactly what is shown over here. If you're having vanadium oxide, the capacity is around 225, whereas the moment you use a nickel doped system, what you find over here is that the capacity, the specific capacity is increasing up to almost 280 milliampere hour per current. So then the effect of the state, the amorphous state on electrochemical potential of electrodes. So mesoporous amorphous materials, they are conducive to the full infiltration of the electrolyte, which reduces the migrating distance of the lithium ions, facilitating lithium ion exchange across the interfaces, and tolerate the large volume change of the electrodes during lithium ion insertion extraction. And these factors greatly enhance the lithium ion storage kinetics and structural stability. So if you look into the current status of LIB, the commercial lithium-ion technology is largely limited to cells with gravimetric energy densities of less than 250 watt-hour per kg and volumetric energy density of less than 650 watt-hour per liter. So the target which you have is around 500 watt-hour per kg and greater than 1000 watt-hour per liter. So you can increase the cell voltage. And how you can do that is by raising the operating voltage of the cathode, as the graphite anode operating voltage is already close to that of lithium plus. So you can only play around with the cathode. And the cathode surface with operating voltage greater than 4.3 volt is not stable in contact with organic solvents which you are having in the electrolytes, which is the ethylene carbonate, diethylene carbonate, dimethyl carbonate, etc., which is used in the electrolyte. So examples of potential candidates with higher operating voltage are the spinel ones, that is LiMn 1.5, Ni 0.504, which is around 4.7 volts, olivine lithium cobalt phosphate, which has a voltage of around potential of around 4.8 volts, and layered NMC with operating voltage of greater than 4.3 volts, reversibly extract or insert more lithium. Or else you can develop new liquid or solid electrolytes with desired characteristics, which will enable the utilization of high voltage, that is greater than 4.3 volt cathodes. Then you can also increase the charge storage capacity. That was all about increasing the cell voltage. The other is, of course, you can increase the charge storage capacity. While the capacity of insertion reaction electrodes, this is limited by the number of crystallographic sites available for reversible insertion extraction of lithium. Conversion reaction electrodes do not have such limitations. So you can have various conversion reactions with which you can also have some alloying reaction taking place. And if all these take place together, in that case, you are going to increase the charge capacity. Why? Because that N value, if you remember that how we calculated the specific capacity, that N value, the number of electrons transferred is going to increase, or the number of lithium ion transferred is going to increase. So the major challenges with the conversion reaction anodes are the huge volume changes up to 400% depending on anode and the lithium content compared to less than 10% for graphite occurring during the charge discharge process, pulverization of the particles, continuous formation of SEI, and the consequent trapping of active lithium from the cathode in the anode SEI. So these are the major challenges you have. So what are the different methods tried to, to increase these or to take care of all these challenges? You can reduce the particle size to nano size or deliberately leave space within the active material architecture. So this will drastically, but the problem is going to be that it is going to drastically increase the SEI formation and decrease the volumetric energy density. So the only progress seen so far is incorporating a little percentage of silicon into graphite to increase the charge storage capacity marginally in the practical cells. So you can use a little bit of silicon doping in this kind of graphite anodes. So the current lithium-ion technology based on insertion reaction cathodes and anodes, it will continue for some time in the foreseeable future, despite their limited energy density dictated by the number of crystallographic sites available, as well as the structural and chemical instabilities at deep charge. So much effort is being made towards conversion reaction anodes and cathodes, as they offer up to an order of magnitude higher capacities than insertion reaction electrodes, but their practical viability is met with many challenges. Renewed interest in employing lithium metal as anode and replacing liquid electrolytes with a solid electrolyte has emerged recently as a good choice, because they can offer safer cells with higher operating voltage and charge storage capacity. But only time is going to tell about their practical viability. So what is a feasible near-term strategy is that to focus on high nickel layered oxide cathodes, liquid electrolytes compatible with and forming stable SEI on both graphite anode and high nickel cathodes. Innovations in cell engineering to fabricate thicker electrodes and reduce inactive components, and novel system integration to realize safer, long life and affordable systems. So if you look into the various kind of anode systems, what you have, the usual processes are this insertion ones, where you have this graphite or you have this Li4, Ti5, O12 kind of these anodes. You can have alloying kind, these are commercialized, but they are like you can have bismuth or you can have tin. So these are all the alloying kinds of anodes you can have. They are very high capacity, but the volume changes are too much, around 400% volume change. So the cyclability reduces because the electrodes kinds of peels off from the layer of the copper foil or the aluminum foil, whatever you're using. And of course, then under development is the conversion anodes. They have large capacity and they do have voltage hysteresis also. So parameters that needs to be considered in adopting lithium-ion batteries for various applications is energy, power, charge discharge rate, cost, cycle life, safety, and environmental impact. So in case of electric vehicles, energy density needs to be really high. Portable electronics, energy density needs to be very high. Whereas if you look into grid energy storage, then energy density can be a little less. So energy density, cost, cycle life, safety, all are important factors. But in case of electric vehicles and portable electronics, energy density really needs to be very high. And of course, it is desirable to have a fast charge discharge rates for all the three different applications. So then coming to cell characterization, first we will talk about cyclic voltammetry. Whenever you are preparing these kind of coin cells in lithium-ion batteries, you are using something which is known as cyclic voltammetry. So this is commonly employed. Cyclic voltammetry, I've anyway always heard about this term because it is commonly employed to investigate the reduction and oxidation processes of molecular species. And CV is also invaluable to study electron transfer initiated chemical reactions. So there are two conventions. One is the IUPAC and the US convention. When you have this US convention, you are moving from high potential to low potential, and the top part is reduction, bottom is oxidation. Whereas when you're talking about IUPAC convention and you're moving from low potential to high potential, basically, the thing is that you're actually applying from the higher potential, you're moving to lower potential, and what you get first is reduction. And when you're moving from the low potential to high potential, what you get is oxidation. So this is the IUPAC convention. Most of the time we use the IUPAC convention. The arrow indicates the beginning and sweep direction of the first segment or forward scan, and the caption indicates the condition of the experiment. So now let's see simple cyclic voltammetry by using reduction of ferrocenium or ferrocenium abbreviated as Fc plus to ferrocene, and you're using a simple chemical reducing agent which is cobalt COCP star 2. So this is what you're using, dicyclopentanediol cobalt. So this you're using as a chemical reducing agent, and with this at the electrode what you see is Fc plus is taking in electrons and it is forming Fc. So now if you look into the current versus potential curve over here, what you see is how basically the current is increasing from point A to B to C, then it decreases to D, then it again increases on the opposite direction. The current is increasing from E maximum, it reaches F, and then it again decreases to the point G. So what is actually happening when you are starting from A to D, you are increasing the potential. From D to G, when you are moving, you are decreasing the potential. And with this, what you're finding is over here, this A, B, C, D, E, F, G, what the small graph this is showing you basically the concentration profiles, where blue is for the Fc plus ions, whereas in case of green is for Fc, that is ferrocene, as a function of the distance from the electrode D from the electrode surface to the bulk solution at various points during the voltammogram. So you see over here how the concentration is changing. In this case, A concentration is maximum, whereas the Fc plus concentration is maximum, whereas Fc is 0. And gradually, as you keep on changing the potential, then the concentration keeps varying. And this is what gives rise to this particular current, whatever you see as per the Nernst equation. So there is an equilibrium between the ferrocenium and ferrocene, and this is described by Nernst equation. So in application of the Nernst equation to the one electron reduction of ferrocenium to ferrocene, the activities are replaced with a concentration which are more experimentally accessible. And the standard potential E0 is replaced with formal potential E0 dash, and N is set equal to 1. So you have this particular equation, and the formal potential is specific to the experimental conditions employed and is often estimated with the experimentally determined E-half value. So when the potential is scanned during the CD experiment, the concentration of the species in solution near the electrode changes over time in accordance to the Nernst equation. So you have something like this. The volume of solution at the surface of the electrode containing the reduced ferrocene called the diffusion layer continues to grow throughout the scan. This slows down mass transport of the ferrocenium to the electrode. Thus, upon scanning to more negative potential, the rate of diffusion of ferrocenium from the bulk solution to the electrode surface it becomes slower, and it results in a decrease in the current as the scan continues from C to D. And the ferrocene which is present at the electrode surface is oxidized back to ferrocenium as the applied potential becomes more positive. At points B and E, the concentration of ferrocenium and ferrocene at the electrode surface are equal, following the Nernst equation, and this corresponds to the halfway potential between the two observed peaks C and F, and provides a straightforward way to estimate the E0 dash for a reversible electron transfer. Now you have to remember these two peaks are separated due to the diffusion of the analyte to and from the electrode. So if the reduction process is chemically and electrochemically reversible, the difference between the anodic and the cathodic peak potentials, called peak-to-peak separation, is 57 millivolts at 25 degrees centigrade, which is nothing but 2.22 or 2.22 RT by F. And the width at half max on the forward scan of the peak is around 59 millivolts. Whenever there is a low barrier to electron transfer, that is electrochemical reversibility, the Nernstian equilibrium is established immediately upon change in the applied potential. By contrast, whenever there is a high barrier to electron transfer, that is, there is electrochemical irreversibility, then the electron transfer reactions are sluggish and more negative or positive potentials are required to observe reduction oxidation reactions, and this gives rise to a very large peak-to-peak separation or delta EP value. Okay, so then we come to the importance of the scan rate. So whenever you are doing CD, you are using a particular scan rate. Now what happens if you change the scan rate? So what is scan rate? The scan rate of the experiment, it controls how fast the applied potential is scanned. Faster scan rate will lead to a decrease in the size of the diffusion layer, and as a consequence, higher currents will be observed. And this is given very nicely by the Randall-Sevcik equation as shown over here. So for electrochemically reversible electron transfer processes involving freely diffusing redox species, this is the Randall-Sevcik equation, and it describes how peak current, this is IP, it increases linearly with the square root of the scan rate, which is nu over here, the square root of the scan rate, and N over here is nothing but number of electron transferred in the redox event. A is the electrode surface area, D0 is the diffusion coefficient of the oxidized analyte, and C0 is the bulk concentration of the analyte. So now for an electron absorbed system, this is how it is going to look. The different solvent characteristics, as you can see over here, this is not very important. We will not spend much time on this. So what we will go into right now is basically how we measure the open circuit potential. So when the cell is assembled and the analyte has been added, a potential develops at the electrodes. For example, when this kind of ferrocenium is added to a cell, the potential of the electrodes equilibrates with the solution, so no current is flowing. The potential observed when no current is flowing, this is known as open circuit potential or OCP. And this OCP, it can give information about the redox state species in the bulk solution as well as concentration of different species when the solution contains a mixture. So now how you minimize the ohmic drop? Electrolytic solutions have an intrinsic resistance in the electrochemical cell. While some potentiostats can compensate for most of the solution resistance, there remains a portion of the uncompensated resistance between the working electrode and the reference electrode. A telltale sign of ohmic drop in CV is increased peak-to-peak separation in the voltanogram for a redox event that is known to be electrochemically reversible. So what happens is that when you're having a voltanogram in which basically the peak-to-peak separation keeps on increasing, this basically shows that there is an ohmic drop which is happening and that you have to take care of. So how you mitigate it? You diminish I, you reduce the size of the working electrode or restrict the experiment to very slow scan rates. You decrease the intrinsic resistance and therefore you decrease the entire resistance in the electrochemical cells by increasing the conductivity of the solution with higher electrolyte concentrations. Or you decrease this RU directly by diminishing the distance separating the reference and the working electrodes. So what is the advantage of CV? It is possible to know whether the chemical reaction of the reactants is reversible or irreversible. The potential at which an oxidation or reduction reaction occurs, that also can be determined. Quantitative analysis is also possible for substances whose concentration is not known. And it is possible to measure by changing test conditions such as scan rate, temperature, and concentration of reactants. You can actually find out the changing, you can find out basically all this different quantitative analysis by changing the scan rate, temperature, as well as concentration of the reactants. So now if you look into how a CV whereas dq by dv plot looks, what you have is, if you are having this kind of a CV plot, when you're having a reversible reaction, it is going to look like this, whereas which is quasi-reversible, the reaction looks like whatever you see in B, and whereas if it is irreversible, then the plot is going to look like this. So immediately by looking into the CV, you can have an idea that whether the electrochemical reaction is reversible, quasi-reversible, or irreversible as per the plots shown over here. So equations of voltammetry for intercalation system. So in a reversible process, since the rate of the electron transfer is rapid enough at the surface of the electrode, the peak potential EP is independent on the variation of the scan rate. Okay, so it is independent of scan rate V. And that is why EP minus EP by 2, this is nothing but 56.5 pi n MV at 298 Kelvin. Now in a quasi-reversible process which shows limitation of electron transfer kinetics, the peak potential then it becomes a function of the scan rate. Now you have to remember lithium intercalation reactions, that is when you're having this lithium intercalation in the graphite, they tend to follow a quasi-reversible process since cathodic and anodic peaks, they are dependent on the scan rate. So CV of quasi-reversible process shows gradual peak shifts to higher potential values with an increase of scan rate than one of reversible process due to overpotentials. The moment you have a quasi-reversible process, what happens is that then you increase the scan rate and you will find your peak is shifting to higher potential value gradually with increase of the scan rate. And this immediately will tell you that your particular system is quasi-reversible. So to obtain the exact lithium ion diffusivity, two boundary conditions should be considered according to scan rate. So if you have a semi-infinite diffusion process, which is a fast scan rate, in that case, this peak current is proportional to the square root of the scan rate. Whereas if you have a finite diffusion process, which is a slow scan rate, in that case, it is directly proportional to the peak current is directly proportional to the scan rate. So if you consider the different diffusion behaviors induced by the scan rate, this is the actual original equation, a very complicated one, though you need not remember. You just have to remember the semi-infinite diffusion process and the finite diffusion process. There's a fast scan rate and a slow scan rate. And what you will find over here is this particular thing, that the peak current in one case, that is when in the faster scan rate, it is proportional to the square root of diffusion, whereas as the square root of the scan rate, whereas the peak current is directly proportional to the scan rate in case when you're having a slow scan rate. Okay. So in a battery system, the electrochemical reactions, they occurs in the electrode through consecutive processes. And so the current obeys the power law, I is equal to A nu to the power of B. So I is the current A and nu is the scan rate, and A and B, they are all adjustable values. So B is the sum of Faradaic or diffusion controlled and non-Faradaic, that is capacitive currents. So if it is only a diffusion controlled reaction, the observed current is proportional to the square root of the scan rate according to the Randall-Sevcik equation. Capacitive current, also called the non-Faradaic or double layer current, in that case, it is directly proportional to the scan rate. So capacitive current is dominantly measured at a fast scan rate, whereas diffusion control current is dominantly measured at a slow scan rate. So the takeaway point from this is this, that whenever, see, there are two contributions which are happening when you are talking about, the electrochemical reaction which is happening in LRB. So you can have a diffusion controlled current, the current which is coming in the CV, it can be diffusion controlled or capacitive controlled. When you're having a faster scan rate, the capacitive current dominates. When you have a slower scan rate, the diffusion controlled current dominates. So now how will you get that B? So you have this power law, now I is equal to A nu to the power of B. So how will you get that B? The B value of total electrochemical reactions composed of diffusion controlled and capacitive reactions, it will have values between 0.5, which is the diffusion controlled, and 1, which is capacitive. So you have this I equal to A nu to the power of B, and in this particular case, what you have is that this B value is going to be given by the slope of this plot, which you will have log I versus log mu, and this slope is going to give you the B value. And you can estimate the capacitive and diffusion controlled currents. So the total current at a specific potential is the sum of both diffusion controlled and capacitive reactions. So I is K1 nu plus K2 nu to the power of half. And then you just do this numerical juggling. You can work it out on a pen and paper later on. And you will find that if you are plotting the scan rate versus this IV to the power of half, what you will get is the slope, which will give you this K1 value. So you will get the total amount of current which is coming from diffusion and the amount of current which is being contributed by capacitive measures. Okay. So estimation of diffusion coefficient through voltammetry. So you can use this particular equation. You can just, if the kinetics of the electrochemical reaction is only controlled by a single phase diffusion without phase transition, the oxidation and reduction currents should have a linear dependence on the square root of scan rate. So this equation, whatever you see over here, is only valid when the phase does not undergo phase transformation during lithiation delithiation process. So it should be a single phase diffusion, not a multi-phase diffusion. The diffusion coefficient using your voltammetry reservoirs. Okay. So you can also determine specific capacity by voltammetry. When calculating the charge storage in a cyclic voltagram with an asymmetric shape of the cathode and anodic peaks, it is usually possible to obtain the integrated area of the cyclic voltagram. And so you can use this kind of integral equation and you can find out basically what is the capacitance and what is the charge. So what are the factors which affect the shape of voltammetric curves? One is the particle size. So size reduction induces an increase in the interfacial area of the particles. That is, the contact area with electrolyte increases and shorten the diffusion length. So as a result of enhancement in kinetics of redox reaction, the overall peak current increases at the same scan rate in the cyclic voltamegrams. So if you have this lithium ion phosphate nanoplates and microplates having different particle sizes at various scan rates, you will find that this value is definitely much more. So when you are increasing the scan rate, you see how basically the slope value is changing. Okay. So this shows you that the shape, the particle size, it affects the shape of the voltammetric curves. Then electrode thickness and scan rate. Okay. For the thin electrode condition, the entire portion of the electrode is in uniform state and electrochemically active. So the peak split changes are not so large. This means that both the surface and the bulk structure of the electrode have a uniform potential and they are homogeneous. Whereas if you have a thick electrode, with the scan rate increase, it shows a very large peak split compared to the thin electrode. Since lithium ion diffusion from surface to bulk, it becomes more difficult. And the bulk potential of the electrode depends on distance from the surface, which causes the potential to drop, which is evident here in this figure. So you can see over here. And also temperature also, it affects the shape of the voltammetric curves. So you have to understand the peak current arising from a diffusion controlled reaction is significantly affected by operating temperature. Capacitive current is essentially independent of the temperature. So a small peak split at high temperature indicates that diffusion controlled reaction dominantly occurs at the surface of the electrode. And the rate of electrochemical reaction depends on lithium ion diffusion in the lattice of the active metals, and this diffusion process is temperature sensitive. So when the peak split decreases at high temperature, it indicates that the rate of electrochemical reaction becomes faster and the corresponding redox peaks can appear early. So this is how temperature affects the shape of the voltammetric curves. So now coming to a few definitions, terminal voltage, as I said, voltage between the battery terminals when load is applied. Open circuit voltage is voltage between battery terminals when there is no load. Internal resistance is overall resistance within the battery, which varies with charge level and temperature and generally differs with charging and discharging. So you have to remember the battery efficiency decreases as internal resistance increases, and this extra charging energy it gets converted to heat, and then ultimately it can lead to a thermal runaway. And battery capacity is the amount of electric charge it can store in a specific condition, measured by discharging a fully charged battery through a load at a constant current rate. So now the capacity of a battery, you have to remember, it usually depends on the discharge condition, how you are discharging, what is the current rate, what is the temperature. So all this will give you the capacity of a battery. So battery will have a theoretical capacity, but how much capacity is actually giving depends on all these different rates. So then you have something which we do when you have a coin cell or lithium-ion battery, you do charge and discharging state test. So what is this? The voltage increases steadily while charging the battery. So you can see over here, this voltage over here, it is increasing steadily when you are charging the battery. Okay. So during this step, lithium ions are extracted from the cathode and they intercalate into the anode's graphite layers. And then the cell is potential statically held at 4.2 volts after reaching the upper voltage limit. This step lasts until the current reaches 0.4 milliamperes, which corresponds to a C rate of 0.01. And this ensures that the battery is fully charged. The battery state of charge at this particular point is 100%. Now the voltage initially drops at the beginning of the discharge, and according to Ohm's law, this voltage drop, also called the IR drop, is directly proportional to the equivalent series resistance. So delta U is I into the equivalent series resistance. So this equivalent series resistance is sums up resistance from the electrodes, electrolyte and electrical contacts. The lower the voltage drop delta U, the higher is the maximum output energy E that can be drawn from the battery. So the limit of a battery's usable capacity is reached when the voltage declines sharply. As you can see over here, when it is sharply declining, that means the voltage usable capacity has been drawn up completely. So the discharge step is generally stopped at around 2.75 volt in case of lithium-ion battery. At this potential, the state of charge is defined to be 0% and the depth of discharge is 100%. So this term C rate, what we use, describes how fast a battery is charged or discharged. The batteries used for this application mode, they have a rated capacity Q of 40 milliampere hour for a 0.2 C rate. So this means ideally you can draw 8 milliampere for 5 hours according to the following equation. So 0.2 C rate means what? 40 milliampere hour, and you can take it for 5 hours. So for 5 hours, it will give you a current of 8 milliamperes. So this is basically the idea of charge and discharge testing. So when you cycle a battery, this is how it is going to look. You cycle the battery over here. You please see this particular plot. This is the cycle value. I'm cycling it for 100 cycles. And this is the capacity. So for every charge and discharge, this is the capacity which your battery is giving. So you can see that basically it is more or less constant. There's a slight drop over here because a little amount of the lithium is getting lost. It is not coming back. And that is the reason why you see this. But this we should say is a pretty good constant cyclability, which is being shown by a battery which is cycled in this form. So batteries are charged and discharged like this several hundreds of times, and then the capacity is measured. Okay, so with this, I will complete the class today. You can go through all these slides, and if you have any doubts, you can mail to me or you can ask your doubts in this class. Thank you.